In this video, I'll tell you what this circuit analysis class is about and what you can expect to cover. I'll also give a really broad brush description of the main categories of the circuits we'll learn to analyze. This can help you put the individual units of the course in the context of the overall class. This class is, fundamentally, about mathematical modeling of engineering systems. Mathematical modeling is used in all engineering disciplines. Classes such as statics, fluid mechanics, heat transfer, and structural vibrations all include math modeling. In this course, the systems of interest will all be electrical circuits. Mathematical modeling is the process of writing and solving the equations that describe a system's behavior. This process is usually referred to as determining the response of the system. For electrical circuits, the response consists of voltages and currents for various components in the system. From a practical standpoint, being able to predict the response of a system is vitally important in engineering. These predictions provide confidence that the engineering system will do what it's supposed to do. One approach to categorizing the math we need to use to model a system is to relate it to the energy in the system. Static systems have either no stored energy or any stored energy is constant. Static systems are relatively easy to analyze. They're governed by algebraic equations. These are the types of circuits that are covered in units 1 through 6. Dynamic systems are those where the stored energy in the system changes with time. These types of systems are covered in units 7 through 12. Dynamic systems are modeled using differential equations. We'll use what are called lumped parameters models for our circuit elements. So the equations we will be writing and solving in this class will be ordinary differential equations. In units 8 and 9, we consider systems with constant forcing functions. In units 10 to 12, we'll be looking at a system's response to sinusoidal forcing functions. Now let's look in a little more detail about the progression of the class. We'll start out with some basic concepts that apply everywhere, such as voltage, current, and electrical power. This will include a discussion of the equations that are used to describe the components in the circuit. These take the form of a relationship between the voltage and current at the element's terminals, so they're commonly called the IV relationships for the component. The sign conventions associated with the IV relationships are absolutely essential in understanding circuit analysis, so they're worthy of a specific mention here. We'll also introduce the IV relationships for power sources and resistors early in the class. The IV relationships for all of these circuit elements are algebraic equations. For example, resistors are described by Ohm's law, which is one example of a circuit element IV curve. The next topics will be the rules governing the interactions among circuit elements. These are called Kirchhoff's voltage law, or KVL, and Kirchhoff's current law, or KCL. These concepts are all introduced right away in Unit 1. These tools are fundamental, and they are all that is absolutely necessary to analyze any circuit consisting only of resistors and power supplies. However, relying strictly on these basics can make the analysis very tedious and time-consuming. Over the next few units, we'll introduce what I call secondary analysis methods. These analysis approaches are all fundamentally based on KVL, KCL, and the circuit element IV relationships. But they are somewhat streamlined to simplify analyses. These analysis methods are presented in units 2 through 5. In those units, I won't really teach you anything new, but I will teach you how to more efficiently apply what you learned in Unit 1. In Unit 7, we'll start talking about energy storage. There are two electrical energy storage elements, capacitors and inductors. The IV characteristics for these elements contain derivatives, which describe the rate of change of energy in the elements. That means that application of KVL and KCL, or any of our secondary analysis approaches to circuits containing energy storage elements, result in a mathematical model that includes differential equations. As I've already mentioned, we'll only be interested in two types of inputs to dynamic systems in this course. First, we'll look at the response of first and second order circuits to constant inputs. These analyses will include arbitrary initial conditions and will determine the complete response of the circuit as a function of time. So these analyses are said to be in the time domain. These concepts are presented in units 8 and 9. Finally, we'll analyze the steady state response of electrical circuits to sinusoidal inputs. The steady state response is the circuit response after any initial conditions have died out, which makes our job a lot easier. In this case, the response can be interpreted as a function of the frequency of the sinusoidal signals. So this analysis is said to be in the frequency domain. These analyses are covered in units 10 through 12. This material will give you plenty of background to analyze more complex systems in later detail. In order to do so, you need to have a thorough understanding of the major concepts of the course. Now let's talk about what kind of background I recommend that you have before taking this course. Generally, I won't expect that you know anything about electrical circuits or circuit analysis. If you've had a physics class that talks about electricity, that's great. If not, it shouldn't be a big deal. However, since there's a fair amount of math in this class, I do assume that you have some math background. The math prerequisites and co-requisites are what I'll focus on here. All of the systems that we'll cover in this class are linear, so we won't be dealing with nonlinear equations, which is a huge relief. As I've already mentioned, static systems are governed by algebraic equations. Engineering analysis often boils down to writing n equations in n unknowns. Circuit analysis is no exception to this, so the equations governing our static circuits will consist of systems of linear algebraic equations. I'll assume that you know how to solve these types of equations. Use whatever approach you want, including a software package that does linear algebra for you. Dynamic systems, in which the energy in the system changes with time, are governed by differential equations. We'll use lump parameter circuit element models. Since our circuit elements will all be linear, and we'll assume that the circuit properties don't change with time, the governing equations will be linear ordinary differential equations with constant coefficients. These differential equations are relatively easy to solve, so I'll tell you all that you need to know about them for the specific cases we'll see in this course. For that reason, I don't consider a differential equations class to be a prerequisite for this course, but it can be helpful. Finally, let's talk a little about how much effort you might expect to put into this class. The material in this course corresponds to roughly a 3-credit, 1-semester class. That should give you an approximate idea of how much effort you might want to expend. Make sure that you work efficiently in the course to maximize the return on your invested time. The feedback that the website is giving you can help identify the level of effort you should be expending. You probably don't need to work every single practice problem and look at every example in order to become proficient. The quizzes are a particularly important component of that feedback. They're designed to indicate how well you understand the material. Remember that you can always come back to a lesson later if you need to brush up on a topic. Since important concepts show up repeatedly, you'll get plenty of chances to learn the necessary skills throughout the course. This was a really brief tour of the types of learning materials available on the website. The examples link in this lesson provides more detailed information about site navigation, the assistance tabs, and how your progress is calculated.